So we got to do a few sections from chapter 10, and then we'll start hitting the review a little bit harder. But you guys should be like Matthew and be kind of working on those AP practice exams as we're working on this stuff. Okay. So basically, what we have going here in chapter 10 is solving word problems with integrals. Okay? Remember we did a bunch of word problems with derivatives? Do you remember that? We did all those maximum and minimum problems, and the water was flowing out of tanks, and people were crossing rivers, and we had to figure out, minimize their time and all that kind of stuff. And so we're doing the same thing now for a little bit with integrals. Okay? So chapter 10 is called Differential Equations. When you guys grow up and go to college and take some math classes, there's actually an entire math class on differential equations. And it is a little nickname called DiffEQs. So if you hear kids in college talking about
no, if we talk about DiffEQs.
My DiffEQ class is really really hard. You'll go, okay, I know what that is, and I can't wait to take it. All right. Okay, so we are on. You might be good for you to turn to be like Shad and turn to page 603. And this is the great contradiction of being a math teacher. You guys always get mad at me when I teach you stuff because you're always like, when are we going to use this? When are we going to use this? When are we going to use this? And when I show you when you're going to use it, then you hate it because it's really hard. Okay? So this is a case of that today. So our little introduction to the chapter says, perhaps the most important of all applications of calculus is to differential equations. When physical scientists or social scientists use calculus, more often than not, it is to analyze a differential equation that has arisen in the process of modeling some phenomenon that they are studying.
Look at this.
Modeling phenomenon.
Which one of us?
Modeling phenomenon.
Ooh.
Although it is often impossible to find an explicit formula for the solution of a differential equation, we will see that graphical and numerical approaches provide the needed information. Okay? So the first example that we are going to look at is...
Hold on. Could you imagine me on the cover of Science Today, like a magazine?
Kind of.
Telling me.
Get some glasses and a lab coat.
Yeah, Science Today.
Really ought to do it.
What's that? Chad would probably be the most likely candidate.
To be on the cover.
To be on the cover of Science Today. Is that even a magazine?
For like a mass murder of blowing up some school because I was trying to do something.
Okay. So that threat that you just made,
It wasn't a threat.
we
It was
have
like,
evidence. So we're recording.
No, I was trying to like make something, like do something in class, and it was
Yeah.
wrong.
It's kind of like being in the airport, being in the security line and making a joke about, some sort of bomb in your backpack. We don't take those things lightly.
I'm going to mix this lotion and toothpaste together and blow up the airport.
So, Mr. Gonna blow up the school, why don't you go talk to Mr. Pugh right now, okay? All right, so you might be asking yourself, what in the world is a differential equation? It doesn't seem like you're probably asking yourself that.
No.
Okay, so did Korea try to bomb us or something?
No.
No, they
Excited,
they stayed at war with South Korea.
They've been at war in South Korea, though, since 1953. The Korean War was never ended. They just had an armistice or whatever it's called, where they just agreed we're not going to kill each other for a little while, but they never signed an official peace treaty. So
Seriously, they said.
technically, the Korean Peninsula has been in the state of war for the last 60 years.
Honestly, though, the guy, he did.
So apparently, some of you are asking yourself, what is a differential equation? Others are asking, what is going on in North Korea? I don't know. Okay.
I think it's South Park.
A
Yeah,
differential equation
equation.
is an equation, obviously. You don't have to write this down necessarily. That not only contains an unknown function. It's an equation that contains an unknown function and that's a D, and some its derivatives. Okay? So it's a regular old equation, but instead of just having like
Oh.
Not in my house.
instead of just having an X or a Y in there, it's got some derivatives in there too, okay? And so to solve a differential equation, since it's got derivatives in there, what do you have to do? If you're gonna, right, you have to take the integral, you have to take the antiderivative. And that's self-guarded. That's no big deal, because derivatives and integrals are inverses of each other, right? So just
Yeah.
like you would solve the equation x plus 2 equals 4 by doing the inverse operation of adding 2, if you had an equation with a derivative in there, you would just do the antiderivative to get rid of the derivative part. Okay? Ready? Thumbs? Wing sing?
First name.
It is the first day back. Okay, so the first kind of model that we're going to look at that answers the deep burning question whether we were going to use this is the model of population growth. Okay? Yeah. One model for the growth of the population is based on the assumption that the population grows at a rate proportional to the size of the population. That is a reasonable assumption for a population of bacteria or animals under ideal conditions. And so what we've got going here is we've got a couple variables. T, of course, is time. And just to be difficult, we're going to let P equal
Number of individuals in the population.
number of individuals in
He
the
got lucky.
population. Yeah, he got lucky. Okay, so T is time and P is population. Okay, all right, so it says the rate of growth of the population is the derivative dp dt. Does that make sense? If P is population and T is time, then if we took the derivative of the population with respect to time, then what we would be finding is the rate at which the population is changing. We're going to assume that it's actually growing.
So what's
Okay?
like the real thing?
We'll get to the numbers in a second, okay? And so the rate of change of the population is going to be some number k times the population p, okay? So the population is increasing. What's going to be true about k? Yes,
Positive.
positive and
Proportion.
greater than 1. Good. If the population is decreasing, then k would be less than 1. Okay, where it says where, and like Nate said, k is the proportionality constant. Okay. Blah 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 blah.
New hit nonsense.
All right, so here's where things get a little wacky. You ready?
Yeah.
Okay. Equation 1, this one right here. Equation 1 asks us to find a function whose derivative is a constant multiple of itself. Well, what function is a derivative whose constant is a constant multiple of itself? No, because the derivative of 1 or 0 is just like 0. Well, we want
X.
No, because the derivative of x is not a constant multiple of itself. And what they're saying is if you answer that question by saying the answer is x, then you would have to say that the derivative of x is like some number times x. And that's not true.
X squared. What?
No, because then if you said this is x squared, then the derivative would have to be some number times x squared.
Negative?
Nope, looking at it, have a look on your face. What's the function that's the derivative of itself?
Oh,
X over T.
E, yeah, because if you take and make this be e to the kx, then the derivative of that is k times e to the kx, okay? So you see how that kind of fits with what we're looking for, okay? So we want to let the population at any time t be equal to c times e to the kt. They have fun yet? Happy to be back? Where did the c come from? It's just a constant. Another constant. Yeah, we got a c, we got a k, we got all kinds of things going on there. All right? So that means if we start with this deal right here, if we want to solve that and figure out what the population is at any time t, this is what we come up with. Okay? All right. I don't know if that makes sense or not.
I think if we go to war with North Korea, they draft.
No. I mean, maybe I'm optimistic, but I think it would be a very short, relatively short.
I think if they were going to go to war with us, they'd need help from somebody. Like, they need help.
Who? Oh, North Korea? Yeah, but China's ticked at them already.
Huh?
China's ticked at them right now. Their dude came out and said, calm down, what is your deal?
Straight down.
Why can't everyone
We
just
don't need to get drafted because they're going to make us.
Why can't everybody just like
be happy?
be happy? None of us do. All right, so then we got a little model for a spring. I'm just going to kind of throw this at you a little bit. We got Hooke's law. You guys know Hooke's law?
Yes,
in
that
physics?
makes sense.
Remember that? Apparently Hooke's law says that the restoring force on a spring is going to be equal to some negative constant times x, and k is the spring constant. Did you guys do a lab? We had to like figure out the spring constant problem.
Yes.
A different spring.
Is that the Barbie?
Then we've got Newton's second law, which is the whole mass times acceleration. We talked about in here, if you start with the position function and you take the derivative, what do you get? Velocity. And if you take the derivative of that, you get acceleration. And so in calculus, instead of doing mass times acceleration, we're going to do mass times the second derivative of the position function, because that is acceleration. Okay, so this is basically mass times acceleration right there. And this equals the negative spring constant times the blah, 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 blah. And the way that they want us to come up with this is, instead of writing it like this, they want to have it solved for the second derivative. So this is our equation for the motion of a spring. Okay? And once again, they don't have any examples of those either. So I can't help you there. All right? What's that? That's probably true.
Where did we get d squared x over?
That's acceleration. So mass times acceleration equals force, restoring force, right? This is F equals ma. Yeah. So this is the force part, is the negative kx, and then that's the, okay? All right, so let's do some examples just for fun. Two examples. So this is kind of weird, but it says, show that every member of the family of functions y equals 1 plus ce to the t over 1 minus ce to the t is a solution to y prime equals 1/2 times y squared minus 1. Okay? What? That means here is a differential equation because it has a function in there and also a derivative. We're going to show that this function right here is a solution to this differential equation. Because when you're solving differential equations, you don't necessarily get numbers as answers, you get functions. Okay? So what we're going to do is we're going to start with this and show that it fits into this format right here. Okay? So I'm going to start by what I have. Y equals 1 plus CE to the t over 1 minus CE to the t. So I'm going to start by taking the derivative because the differential equation has a derivative in it. So how do you take the derivative of that? Nice and almost lost in there. So
Quotient rule.
quotient rule. Okay, so I have to go low,
3 high.
8 high. What's the derivative of this?
TC to TCE
TCE to the CT, what?
TCE.
Yeah. TC to the T.
No, tell me, Langston.
C to the T.
C times E to the T.
Yeah, but don't you have to times it by the thing?
Yeah, what's the derivative of this thing? Just one. Okay. Low D high minus I D low.
Negative C T.
Negative CE to the T over square of what's below. All right, so our job is to take this derivative and make it fit, oh, that's fine, this format right here. Okay? So we're going to do some crazy algebra, and in the end, we're going to turn this whole mess right here into 1/2 times 1 minus y squared. Okay? Ready? Let's multiply some of that stuff out. So if I distribute this, I get CE to the T minus, what do you get when you multiply those two things together?
C to the T squared.
No, sir. Minus times positive is minus. C times C is C squared. Okay? And E to the T times E to the T is
E to the T squared.
E to the
2T.
T squared, which is E to the 2T. Okay? All right, minus, but if I go negative CE to the T times 1, I'm going to get negative, so that's going to be a positive CE to the T, right? And then this negative is going to go through and make that negative. And then that negative is going to go through and make this one positive, so that's going to be plus C squared E to the 2T all over 1 minus CE. Okay, so what happens on top?
2CET.
Right, those things cancel, so I'm left with 2CE to the T over 1 minus CE to the T squared. Okay? Are you sort of wondering what kind of, what did that accomplish? Lord only knows. Wow.
Got stuff. Got a wall now.
Did we prove it? Are we done? No? I'm wondering why we took the derivative of it. Oh, I see. Okay. All right, so that's the y prime, okay? So that is the left side of this right here. We figured out equals 2c e to the t over 1 minus c squared, right? Okay, so now we have to simplify the right side right here. And the way I'm going to do that is instead of taking the derivative, I'm going to take this thing that equals y and plug it in there for y. Okay? Are you, what just happened, Shad? Should I be scared?
Kind of lower those.
You go see you
Yeah.
Okay, so instead of going 1/2 times y squared minus 1,
We'll take a freaking money holder.
I'm going to go 1/2 times,
Come over here, drum out.
Not to mention the guy who
right?
works
You guys with me?
Yeah.
A little bit. So all I did is now I took the right-hand side of the equation and I replaced the y with the 1 plus c e to the t over 1 minus c e to the t. Okay? What? Square it? Pretty hard to square it? What is this thing right here squared? Can you like boil that out in your head? 1 plus,
2C.
good, 2ce to the t plus
C is
c.
T. C is 2T.
Oh, they're not even going there. Oh, they're being tricky.
Yeah, it's 2 squares.
They're doing a difference of 2 squares thing or something.
We don't want to do that.
Yeah, because they've got this squared minus that. It's like 1 squared, so you can factor that out and then things cancel, and then guess what it equals?
0.
2ce to the t over 1 minus. Yeah, so now we're just going to decide to be done because we don't want to do all that. This is what we got for the derivative, and so it works out. Okay?
But how does I get you 1/2?
You be quiet.
Read the book.
Yeah.
Here, read the book.
I don't read
That's what I thought.
All right. I don't even know what just happened.
It's okay.
As you up.
Hold on, I got something for the class. Okay.
What?
It is. You know, there's Blanco. Well, you know who Blanco really is?
Yeah.
There's Blanco. The brother stole
Oh,
Blanco.
yeah.
Anyways. My hot tummy, my team leaves, so my hot tummy got out weekend. And first thing we walked in,